In the future, will wind power tapped by high-flying kites light up major cities? A new study by scientists Ken Caldera at the Carnegie Institution and Christina Archer of California State University identifies prime locations for exploiting high-altitude winds in the jet streams. Jet streams are meandering belts of fast winds at altitudes between 20,000 and 50,000 feet that shift seasonally, but otherwise are persistent. Their winds are steadier and 10 times faster than winds near the ground. The study found the highest wind power densities over Japan and eastern China, the eastern coast of the United States, southern Australia, and northeastern Africa. The median values in these areas are greater than 10 kilowatts per square meter. The analysis included assessments of high-altitude wind energy for the world's 5 largest cities: Tokyo, New York, Sao Paulo, Seoul, and Mexico City. New York has the highest average high-altitude wind power density of any U.S. city, with an average wind power density of up to 16 kilowatts per square meter. For cities such as New York that are affected by polar jet streams, the high-altitude resource is phenomenal. High-altitude winds globally contain enough energy to meet world demand 100 times over. One technological scheme proposed to harvest this energy includes tethered kite-like wind turbines at the altitude of the jet streams. While there is enough power in high-altitude winds to power all of modern civilization, the wind can still be expected to fail about 5% of the time. Constant power would require backup, massive amounts of energy storage, or a continental or even global-scale electricity grid. So, while high-altitude wind may ultimately prove to be a major energy source, it requires substantial infrastructure. The research appears in the online journal Energies. This is John Strom for the Carnegie Institution. At high altitudes, most of the dust in the atmosphere comes from space rather than the Earth. Thousands of tons of interplanetary dust particles, or IDPs, enter the atmosphere each year. Much of the dust is thought to come from comets, which contain primitive, unaltered matter from the formation of the solar system. A team of scientists, including researchers from the Carnegie Institution, have for the first time tied upper atmosphere dust to a particular comet. In April 2003, a NASA aircraft gathered dust samples after the Earth passed through the dust tail of Comet Skellerup.
We got our hands on some of these IDPs that were collected in April 2003, and what we found when we studied them by a large number of techniques is that they're very different from typical IDPs that are found in that they are what we would say is more primitive. They have higher abundances of material that formed before the formation of the solar system. As a result, we believe that since these particles were collected at a specific time and share some very interesting properties that are not typical of IDPs, we believe this ties them to the comet we were hoping to study, Skellerup. And in this way, it allows us to compare on a microscopic scale in the laboratory dust particles from different kinds of comets and use that as a tracer of different processes that occurred in the solar system 4.5 billion years ago.
This interplanetary dust can be compared to the samples returned by NASA's Stardust mission that returned comet dust in 2006.
This is very important because although we've known IDPs come from comets, we've never been able to definitively tie a single IDP to a single comet. And the only known cometary samples we've studied in the laboratory are those that were returned from Comet Wild 2 by the Stardust mission.
The samples provided a number of surprises.
The biggest surprise is the abundance of so-called pre-solar grains. And pre-solar grains are tiny dust particles that formed in previous generations of stars and in supernova explosions before the formation of the solar system, and were trapped in our solar system as it was forming and are found today in meteorites and in IDPs. And they're identified by having extremely unusual isotopic compositions compared to anything else in the solar system. And one important thing about pre-solar grains is that they're generally in very, very low abundance. In these IDPs that are associated with Comet Skellerup, they're up to hundreds of times higher abundances than we've seen in other primitive materials, which means that for some reason these grains have either trapped a higher abundance of them in the very, very earliest stages of solar system formation, or these samples have destroyed grains. These samples seem to be much more primitive, much less processed than the samples from MILD-2, which seems to indicate that there's a huge diversity in the degree of processing of materials in different comets.
The unusual ratio of rare isotopes gives some indication of when the samples were formed.
There's various chemical reactions that can cause these fractionations, but it most likely happened before the formation of the solar system while the material was in a molecular cloud in the galaxy.
The research was reported online in Earth and Planetary Science Letters. This is John Strom for the Carnegie Institution. A team of astronomers led by Carnegie Institution's Masami Uchi has completed a broad survey of galaxies to help pinpoint when an era called the reionization epoch likely began. 13.7 billion years ago, the Big Bang created a hot, murky universe. 400,000 years later, temperatures had cooled enough that electrons and protons could join to form neutral hydrogen, and the murk cleared. Sometime before 1 billion years after the Big Bang, hydrogen began to form stars, which radiated energy and started the reionization epoch by changing hydrogen back to being ionized. The U.S. and Japanese team led by Uchi used the 8.3-meter Subaru telescope to survey an area that is over 100 times larger than previous surveys. Using progressively redder filters, the team was able to watch which galaxies disappear from or drop out of images and calculate galaxies' distances and ages. The survey was able to confirm the age of one galaxy at 787 million years after the Big Bang. The research appears in the December issue of the Astrophysical Journal. This is John Strom for the Carnegie Institution.